Question 6. This question is about induced EMFs. In the diagram below, a thin rod made of conducting material is moved along a conducting rails. As you can see, these are two rails. A conducting wire is moved along the rails at a constant speed. The speed is given 5.5 meters per second. The rails are in a region of uniform magnetic field of strength B that is directed at right angles to the plane of the rails. A conducting wire is connected between the rails as shown. Okay. Now, the distance between X and Y is 0.30 meter. X and Y is basically the length of the rod is 0.30 meters from here to here inside the reel. Okay. The magnetic field strength is 0.2 Tesla and it is going down as we have seen previously. The speed of the rod is 5.5 meters per second. On the diagram above, draw arrows to show the direction of the force on the electrons in the rod. First of all, force on electrons. Let us consider electron, one electron here. Now, since it is electron, a negatively charged particle, we will use our right hand. Right hand Fleming's rule will be used in order to find out the direction of the force. Now, so right hand, in case of negatively charged particle, first is your index finger. Index finger will show the direction of the magnetic field, which should be downwards. Point your index fingers downwards. Second is the motion is shown by middle finger. Middle finger, it is moving towards right, right? So middle finger shows the velocity, direction of velocity, which is towards right. And then you extend your thumb. So thumb will be pointing towards yourself. Thumb, which shows the direction of the magnetic force, will be pointing towards you or out of the page. Out of the page. So force will be applied in this direction. Magnetic force on the electron will be applied in this direction. That's it. Next question is the force on the rod due to induced current. Force on the rod due to induced current. Now here we'll have to apply Lenz's law. Lenz's law says the induced current or induced EMF will oppose the source of it. Basically, motion. Okay. Why current is being induced here? Because of the change of flux. There will be change of, because of change of flux, there will be induction of EMF, which induces current. Now, why the flux is changing? Because it is moving. It is moving, and in this process, it is covering more and more area. So if you remember, flux, the definition of flux is numbers of field lines passing through the cross-sectional area perpendicularly is called flux. And as the area is increasing, flux is increasing. Or I'll say flux is changing with time, which induces EMF, which induces current. Now this current will oppose the change of flux. How? By opposing the motion. Why there is change of flux? Because of the motion, right? So it will oppose the motion. So velocity is in this direction. Hence, a force will be applied in this direction. Fm will be applied in this direction so that it can oppose it. Previously, Fe. I should have written electron on the electron. Force applied in this direction, which is Fe. And on the rod, force applied will be Fm. Okay. So that it can oppose the motion, hence oppose the source of itself. Now calculate the EMF. EMF we know is equal to BLV sine theta. Theta is the angle between magnetic field and length. Magnetic field is pointing downwards, length is perpendicular to it, if you can see. 90 degree. So theta is 90 degree. Sine 90 degree is 1, right? So EMF will be BL into V. Now, what is B? B is magnetic field strength, which is given here, 0.02 Tesla. L is length of the rod, which is 0.3. L is length of the rod. V is velocity, which is given, or the speed of the rod is here. Since we are finding out the magnitude, so we'll consider speed, which is 5.5. Now let us find it out. 0.3 into 0.2 into 5.5. 0.33 volts. EMF is 0.33 volts. So I'll write it here. So 0.33 volts. Second question, calculate the force required to move the rod at constant speed due to an induced current in the rod of this. You see, force applied in this direction so that rod is in equilibrium. Equilibrium means velocity either can be 0 or constant. Okay, so they are asking us to find out this Fm because of the flow of current. Okay, let us assume current is flowing like this. Current is given 0.8 ampere or 0.80 ampere. In that case, force M is equal to BIL. L is length of the rod. B is 0.2 is given here. 0.2. L is 0.3. Current, right? 0.8. And L is 0.3. So 0.2 into 0.8 into 0.3. We get 0.042 Newton or 4.8 into 10 to the power 2 minus 2 Newtons. This is the force. Now they're asking, deduce that the mechanical power required to move the rod at constant speed is 5.5 is equal to value of electrical power dissipated in the rod. Okay. So I'll write down here 4.8 into 10 to the power minus 2 newtons. This is the force applied backwards to resist the motion. First of all, let us find out what is the electric power dissipated. P is equal to VI, that is the formula. But here, V is nothing but EMF. V, potential difference, and EMF, they're equivalent things. So in this case, EMF is induced, right? So P will be EMF into induced current. EMF is 0.33 into induced current is 0.8 watt. 0.33 into 0.8, which is 0.264 watt. This is the electric power dissipated. Electric power dissipated through the rod. Okay. Now, power required to oppose that, the power, mechanical power required to move the rod at constant speed. Mechanical power required to move the rod in constant speed will be, first of all, this FM we have found out. Let me write it. P dissipated is 0.264 watt. Omit this. The FM we have found out is directed towards minus X direction, right? Minus X direction, which is opposing this. So this is the force. Now, equal amount of force must be applied in this direction in order to move it constantly, right? Because the forces has to be balanced in order to reach the equilibrium. So Fm is equal to F. Okay, equal and opposite. So F will be plus 4.8 into 10 to the power minus 2 Newton. Okay, this is in negative direction, negative x-axis. This is in positive x-axis. So this is plus. But their magnitude will be equal. Okay, that's why this force has to be applied forward is this. Now, mechanical power required will be P is equal to work done per unit time, right? Or I'll write work done by del T, time interval. Now, work done is force into displacement along positive axis in this direction. Let us consider it as displaced to this distance D. Okay. Divided by del T. Now, distance by time. Or if you are considering displacement by time. Displacement by time is nothing but velocity, right? So I can write P is equal to F into V. Now what is F? Required is 4.8 into 10 to the power minus 2 newtons into velocity is 5.5, isn't it? 0.048 into, or 4.8 into 10 to the power 2 minus 2 to 5.5. It's going to give you 0.264. This is the mechanical power. I can write this is electrical power dissipated. This is the mechanical power. You can see both of them are 264.264 watts, right? PM is equal to P. Mechanical power required is nothing but the power getting dissipated as thermal energy. We are able to show that.